I'm Meghamala, working assistant professor from Electronics and Communication Department, Institute of Aeronautical Engineering. And today I'm going to discuss the question bank on decoders. Okay, so the question from the decoders, or else from the using gate level, the question says like this: construct the Verilog code for 823 encoders using gate level modeling. So, in this presentation, we will be discussing more about the encoders and the decoders, how to solve the problems based on using the gate level modeling with respect to the encoders and as well as the decoders. So, this particular question is 823 encoders. So, we are just constructing a Verilog code of 823 encoder using gate level modeling, right? So we all know what is gate level modeling. Gate level modeling is one of the modeling which is defined by in the Verilog, and the keyword assigned with this particular gate level modeling is assign. Assign is a basic keyword which is mentioned with respect to this gate level modeling. Gate level modeling helps us to know the structure of a particular gate, right? That means what? For example, being a designer, if you have designed some product, okay, if you have designed some electronic device, and that device if you are made with that particular designing is made with respect to the gates, different gates. Okay, so we are calling that that such type of modeling is nothing but the gate level modeling. And to require the gates, or else to take in order to construct different elements, in order to construct different modules, we need the gates, right? So these gates can be available in the Verilog primitives, right? So in the Verilog library, the gate primitives which are already available in this Verilog library, and with the help of this gate level primitives, or else gate level primitives, we can easily able to construct the particular design of the building blocks. And now we all know what is an encoder. Encoder is nothing but it is something that if you are giving your input as 2 power n, so that you will get the output as n, right? So this is an encoder. So for example, we have different types of encoder. These are the major building blocks for the electronic devices, where it decodes, okay, it encodes the data. Okay, so that means what? If you have 2 power n inputs of data is encoded as n output. Okay, so in the encoder we have different types of encoders like that. It is 8x3 encoder, 2 power 2. It's right. 4x2 encoder. So like that we have different types of encoders. In this particular example, we will see how can we write a Verilog code based on this 8x2 encoder using gate level modeling. And also one more thing is, whatever the example that you are considering, whatever the circuit that you are considering, the model, okay, the model that you are considering, remember that there are 4 ways to write your Verilog code. Okay, you can write your Verilog code in the behavioral modeling, you can write your Verilog code in the gate level modeling, you can write your Verilog code in the data flow modeling, and as well as we can write our code in the switch level modeling as well. So these are the 4 types of modeling styles, modeling styles in the Verilog. For each and every modeling styles, there is a way of assigning the keyword. Okay, there is a way of writing the code. For example, when it comes to the behavioral modeling, in the behavioral modeling, when you're constructing a Verilog code, in the Verilog code, there is a keyword, basic keyword where you need to assign. So if you are writing your code in terms of behavioral modeling, then remember that always at the rate is a keyword, okay, which is meant to be written with respect to this behavioral modeling. And when it comes to the gate level and the data flow modeling, remember that in your when you're constructing your Verilog code, all assign is a basic keyword which is pertaining to the gate level modeling and as well as the data flow modeling, right? And always at the rate is pertaining to the behavioral modeling. Okay, and then we will see now how can we construct this 8x3 encoder using gate level modeling. The conversion of binary to decimal is done using a device, namely a decoder. So the decoder, it means that it just converts the bits. Okay, it just converts the binary bits to decimal bits. So this is one of the main specifications of the encoder, where it converts a binary to the decimal bits. And this device is one kind of combinational logic circuit that uses n input lines to generate 2 n output lines. So if it is n input lines, we'll observe 2 power n output lines, and then the output of this device might the output of the device shows that 2 power n lines, right? And then some kind of decoders, they include one or more enable inputs. Okay, we can see one or more enable inputs along with the data input. So for whatever it is, the decoder or encoder, multiplexer or demultiplexer, there are few separate lines we can see. Okay, they are the data lines or else selection lines as well. And then whenever the enable input is disabled, then all the outputs will be inactivated. So whenever this enable bit help us to get the output depends, the output purely depends only on the enabling of this enabling bits. So here we will see this is a decoder where it is a combinational logic circuit where it can change it can change the code into a set of signals. Okay, so here it is a reverse process of encoder. Obviously, encoder is opposite to the decoder, right? So it's a reverse process of encoder where what happens is, if you are considering the decoder is nothing but it takes n inputs and 2 power n outputs, right? Whereas the encoder, it takes 2 power n inputs and n outputs. So if it is a decoder, the quite opposite comes under the opposite is nothing but the encoder. Encoder means it considers 2 power n inputs and will observe the output as n outputs, right? And now see, this is a encoder, 8x3 encoder. Here in this particular block diagram, we have 8 inputs, right? 8 input, 8x3 decoder where you have 8 inputs and 3 outputs. So 8 inputs are represented by D0 to D7. Okay, D0 to D7 are the 8 inputs, and outputs are denoted as X, Y and Z. Well, because 8 inputs and 3 outputs, right? And then followed with this logic diagram. We have the logic diagram where this logic diagram is as it has rule with respect to the gates, right? So here we know that 8 are the inputs. So these are the 8 inputs and we know the 3 outputs, 8x3 decoder. So if you observe here, all the 3 gates, right? So all the 3, what sort of gates? These are the OR gates. So all the 3 OR gates are connected to the inputs. So that means what? Here we have 8 inputs. So all the 8 inputs are connected to the 3 basic gate, that is OR gates. With by the segregation of the input, we can able to get the output. For example, here you can see for example here OR1, OR gate 1, OR gate 2 and OR gate 3. So here, in order to get X, Y and Z, these are nothing but the output. So how am I obtaining my output X as? See, I'm getting like D4 plus D5, right? So for this XOR gate 4, okay, D4 is connected, plus D5 is connected, and then D6. So for this D6 is also connected and D7. Okay, likewise I can observe the output as in terms of the 3 X, Y and Z, and this example or this logic diagram is meant with respect to the gate level modeling. Remember that decoder and encoders, these are the basic building blocks where we can convert, okay, binary to decimal numbers, right? Binary to decimal form of the conversions can be created or can be done with respect to this basic encoders and the decoders. So we can see, I can also say that the encoders and decoders are quite opposite to each other. Encoder says that 2 power input to the output. That means for 2 power n inputs and 2 power n inputs, if you are considering, you will observe the output as n, right? So we have different types of encoders, that is 8x3, and decoder is quite opposite. If you are considering n input, then your output must be 2 power n outputs, right? And now this is a truth table. So for each and every basic building blocks like encoder, decoders, multiplexers, we have the truth tables to be considered. So for these truth tables, we have the digital inputs and the binary outputs as well. So we know the digital inputs are, as it is 8x3 decoder. So my I can say my inputs are 8 inputs and the outputs are 3 outputs, right? So 8 inputs. So 8 inputs from 0 D0 to D7 and 3 outputs X, Y and Z. Right? So so this is a truth table where you can say that when my output, see, the D0 will be, D0 is enabled, only D0, okay. Out of 8 bits, only D0 bit is enabled when my all outputs are 0. Okay, and D1 bit is enabled when when D1 is enabled, what happens is my outputs are X, Y are disabled, whereas Z is enabled. Okay, then D2 bit is enabled when my X is disabled, Y is enabled, and then Z is disabled. Likewise, finally till the 7th bit, right? So this is 0 and this is 7. So till 7th bit. So at the 7th bit, my D7 is enabled based on the output I'm getting as X, Y and Z are enabled bits. So when D7 is enabled, the rest all the bits are disabled. And when all the bits are disabled, it says that my binary output would be 1, 1, 1 as X, Z and X, Y and Z. So this is a basic explanation of the truth table of 8x3 encoder. And now we will see, so this is the other Verilog code. So our main theme is like we need to construct the Verilog code of 8x3 encoder in gate level modeling, right? So in gate level modeling. So this is our question. And now, till now, we have discussed what is an encoder, what is a decoder, difference between the encoder and decoder, and also we have discussed like by considering some examples. Okay, so encoder is nothing but 2 power n into n output, whereas decoder is n into 2 power n output, right? So if n is the input, 2 power n will be my output, and if in the encoders, my input would be 2 power n input and output would be n output, right? And now we will construct our Verilog code by using this gate level modeling. So before we go that gate level modeling, we can also write, or else we will construct our code, okay, Verilog code in the structural modeling and data flow modeling as well. This is just to show the similarities, or else this is just to know the difference between the writing of Verilog code in different modules. So now in structural modeling, this is how I can write this Verilog code. So basic and first and foremost thing, before you write your Verilog code is always remember that it should start with a keyword. Okay, so you know the keyword, different keywords we have used in the Verilog Verilog. Okay, so they can also be called as lexical tokens. So these lexical tokens are of 7 types, and out of 7 types, keywords are one of the basic lexical tokens. Okay, keywords are one of the basic lexical tokens. These keywords, based on these keywords, we can able to recognize what sort of the code is written in what sort of code is written in certain modeling styles, right? So now we will see the structural modeling. In the structural modeling, how we have to start with a keyword called module, and then instance name. The name of that particular device that we are constructing is encoder, and here it is a port list. So in the port list, we have to represent our input and output and in outputs as well, and then followed with the input output. So input is 7:0 with respect to the D in, and output is 2:0 with respect to the D out. Okay, and then finally register. Register is nothing but it is a data type. Okay, it's a data type. So what sort of so it's 8x3 encoder, right? So here at the output, how many bits I'm going to achieve is 3 output bits. So 2:3 D out, right? So in the data type register, I'm just locating 3 bits of data with respect to the out. So this is concerned with respect to the output, and then based on the based on the structure. So in the previous slide, we have designed this particular 8x3 encoder using the gate level, right? So here we have used OR gates. So how many OR gates I have used? 3 OR gates I have used. So in the structural modeling, okay, the code with respect to the structural modeling, I have to write OR G1 D output 1 2 3 input 5 7. Okay, so that means what am I doing is this, as it is a structural modeling. So I have to write the output. Okay, I got the output with respect to the OR gate. So the OR gate output is D for OR gate 1. The output is, see, this is OR gate 1 and this is OR gate 2 and this is OR gate 3. So for OR gate 1, how am I writing my output is D4, 5 minus D6 and D7. So see, output as 0, 1, 3, 5 and 7. So likewise, the rest of the OR gates, I'm going to write my code with respect to the second, or this is first OR gate and this is second OR gate and this is the third OR gate. So finally, remember, for each and every statement, the semicolon is need to consider. Without the semicolon, then it says that it's a wrong way of writing your code. And then finally, ending up or else terminating your code with a keyword called end module. So in the keyword, if you are starting your keyword with module, then you have to end with the end module, right? So this is how you have to mention, and this is sort of writing the Verilog code in the structural modeling. And then we'll quickly move on to the data flow modeling. So the data flow modeling is nothing but it is observed from the gate level modeling, where it is the overall structure. Here in the data flow modeling, we have to write the particular Verilog code, that means describing the structure of that particular gate. And now we will see the module encoder, D in and D out as a port list, and then representing input and output, and then a register 2:0 output. So till this extent, in all the structural and as well as in the data flow modeling, they are considered to be same. Okay, and then here starts the difference. So here in the structural modeling, how are we writing the code is, we are directly going out to by considering the gates. Okay, whatever the gates are assigned to us to that particular model. And whereas in the data flow modeling, using the keyword, as I said you, in the behavioral modeling, data flow modeling, gate level modeling and structural modeling. So there are different types of keywords which are need to write in when you are writing your code. So here, as we are writing our code in the data flow modeling, so we need to use a keyword called assign. Okay, assign output 1, 2, 3, 5, 7, and this is what we are writing, and then OR and OR gates. Finally, ending up with the end module. So here, before we writing code, we can also write assign OR gate. Okay, assign OR gate. So for this OR gate, what are the inputs that you are considering and what are the outputs that you are obtaining? Okay, everything we need to mention. So this is one way of representing our code, or is writing our code in terms of data flow modeling. And then we'll move on to the another code, behavioral modeling. So in the behavioral modeling, this is how we can write our code. So here in the behavioral modeling, same like the previous structural and the data flow modeling, the very first and foremost sentence that we have to write is the representation of the keywords like module, encoder, input and output, and same the instantiation of the inputs and as well as the output. Okay, 8:0, 7:0, that is totally 8 bits, and 2:0, that is totally 3 bits of data. And then register is a data type where we are mentioning with respect to the output. And all remember here, see, we are writing a code in the behavioral modeling, so we are representing, okay, the keyword always at the rate. Okay, always at the rate with respect to the D in. And now we will begin. Okay, so as it is a 8x3 decoder, 8x3 encoder, then now we will begin. If my input is 8 bit of 1, then my output goes 0. That means what? Simply, if my inputs are 0, 0, 0, 0, 0, 0, 0, 0, 1, then my output goes like this, 0, 0, 0. Okay, similarly for if else, what? If else is 800 or 000 with respect to 1 and it is 001. So if else, so by using if else if statements, okay, if else if condition, we are going to write our code with respect to the behavioral modeling. And then finally writing from 0 to 7, right? From 0 to 7, finally ending up with else the output is 3 bit. Obviously our 3 output, this is the output and these are the inputs. Inputs are of 8 bits, right? Outputs are of 3 bits. So outputs are of 3 bits. So else D out is equals to 3 bits of data, and finally an end module. So this is how we can write our code in the behavioral modeling. So out of these three modeling styles, you might have observed a little difference between these three, among these three different styles, right? So the very first and foremost thing to remember in your mind when you're writing your code in different languages are the keywords. So each and every module have different types of keywords. If you're writing your structural modeling, there's no need to assign any keyword. Whereas if you are going to write your Verilog code in terms of data flow modeling, then you have to go with a keyword called assign. Okay, assign y input, or else assign the input, 8 bits of data input. And then if you are going to write your code in the behavioral modeling, remember always at the rate. Okay, always at the rate block. So these are the very important points to be remembered. And then finally goes out with the code. We will be writing our code with respect to the truth table, and by using the conditional statement. Sometimes we can write based on the device that you are considering. Okay, sometimes we can go with the first statement. Sometimes we can go with if-else statements. For sometimes we can go with if-else-if statements, so on. Okay, and then finally, don't remember that you have to terminate your code with respect to R and end module. Then this is a test bench. So this is a test bench way of code, test bench Verilog. So here in the test bench, similarly like the previous one, everything will be same, but only few things are differ. Whereas here in the test bench, module keyword encoder register 0 is to 7. Wires, see, wires are meant for the physical connection. So for the physical connection purpose, we are representing with a wires, right? So representing with wires. And then end module, out D, A, B, C, D, C, all the inputs, right? All the outputs. And then finally starting up with the initial begin. And so here at 10 nanoseconds of delay. Okay, at 10 nanoseconds of delay for each and every bits to be enabled. The enabling of bits will be happen for each and every 10 nanoseconds of delay. Okay, and then finally we are stopping right from the 0 to 7. The 8th after 7, what are we doing is we are just stopping the process, because our inputs are 8 by 3 inputs, 8 by 3. Right, that means 8 inputs and 3 outputs. So from 0 to 7 we are going to process with 10 nanoseconds of delay, and later on that we are stopping the process, and then finally writing up with end module. Okay, and so this is a very basic question to be asked in the Verilog, in the Verilog code. By using the Verilog code, we can write for different modules, right? Multiplexer, demultiplexers, encoders, decoders, flip-flops, registers, and so on. So for each and every, sometimes we may ask questions to write our Verilog program or its Verilog code in terms of structural form, or else in terms of data flow modeling, right? So sometimes we may ask to write our code in terms of behavioral modeling as well, or else in terms of switch level modeling. So if you're asked to write your question in terms of gate level modeling, simple thing is first define what is the model. Okay, what is the circuit that you are going to explain it well, and then draw the logic diagram or the block diagram. First mention the block diagram with all the inputs and outputs, and then go with the logic diagram. And after the logic diagram, you just draw the truth table. Based on the truth table, you can able to write your Verilog code very easily. Okay, don't forget to mention your inputs and outputs properly. So this is one of the way of writing your code in the gate level modeling. So in the gate level modeling, we need to mention the gate, what sort of gate you are using, and also in the Verilog code you have to mention it clearly what sort of gates you are using, and or if you are using universal gates, mention universal gates, what are the inputs that it is considering, and what are the outputs that it is giving. Okay, so all these things matters a lot. I hope you understand. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.